You just saw some examples that were not too painful given the formulas, and as long as you know the formulas, you'll be okay. So here we go. Mammalogists are tracking the movement of a rabid skunk through the forest. His position is modeled by that vector from 0 to 10. Distance is measured in meters. T is measured in minutes. So they've been tracking this guy for about 10 minutes, and they know that he's traveling along this path. Let's actually graph it just to get a frame of reference. So y equals. And I'm going to clear out all the other stuff. Actually, let's not clear that one out because I might need some acceleration in a minute. Acceleration for my skunk. Sine of 2t, there's that one. And then t squared over 6 times cosine of t, there we go. And I'm going to graph this on a standard window from 0 to 10. 0 to 10. Now, if I press zoom standard now, it resets my t's. But let's go negative 10 to 10 for the x's and negative 10 to 10 for the y's. And when I do that, that'll give me the standard window range, and then we have set the t values appropriately. So graph. There goes my skunk. Whoa, now, where'd my skunk go? All right, I'm not sure what happened to him down here. Let's find out. When you don't know, you can go to the table. So I want to know what happened at 10. Okay. He was 0.9 to the right and negative 14-ish down. So I'm going to readjust this a little bit here. I'm just messing with it just to figure out what I can do. So negative 15. There goes my skunk. There he is. All right, I'm going to adjust a little bit more. You don't have to do what I'm doing. I just want a better visual for it. I'm going to make this negative 2 to 2. I think it'll be better to see. There goes my skunk running around, kind of pacing back and forth frantically. He runs off and curves around. All right. By the way, people do this kind of thing, and mammalogists, it's a job. Now, do they use these kinds of things to model that? I wouldn't doubt it. I mean, I know those kinds of things are used in other careers. I don't know if mammalogists use them or not. Anyway, find the velocity vector for the skunk. They did not say evaluate it at a specific time. They do here, not here. So let's just find the derivative. You've done it before. Let's go fast. Derivative of sine of 2t would be 2 cosine 2t, comma, and the derivative of this guy, that's going to involve the product rule. So f prime, so 1/6 t squared, that would be 1/3 t, f prime g plus f g prime, derivative of that would be negative sine t, which means I need a negative right here, and that is it right there. We've got this vector that tells us the velocity of this skunk, this denizen of the forest. What we're going to do is find the velocity vector for the skunk at a specific time. So final answer is going to be numerical. And so let's figure it out. Now I'm going to go ahead and do a little trick I did a minute ago with my acceleration. So math 8, the derivative with respect to time of y1. There we go. I could type that in if I wanted to. I don't want to. And then math 8 ddt y1 t equals, well, t. There we go. And there's the acceleration if we need it, but I want to know the velocity vector at 6 minutes. I'm going to go to the table, second table, and I'm going to type in 6. It's not this. That tells me its position. This was displacement. This tells me, almost got stuck on that. It tells me its position, not its displacement. Okay, got it. This tells me its velocity. Sorry, I almost said the wrong thing. I did say the wrong thing. 1.688 and then 3.597. There we go. Total distance traveled. What's total distance traveled? I'm glad you asked. This guy right here. Let's find it. I want to get harder than it is. So here we go. The integral from 0 to 10 of the square root of a whole bunch of big disgusting stuff, and that disgusting stuff is 2 cosine 2t. Please don't try this one at home. Let me rephrase that. Don't try this one by hand. Please try it at home. And then 1/3 t cosine t minus, should write that, minus t squared over 6 sine t. Oops, forgot it there too. My word. My goodness. There we go, dt. And we're going to do this. It's going to take it a minute to figure it out, and I'll type it in super fast. Well, See how fast I can go. Math, 9 from 0 to 10. Total distance this skunk traveled would be x2 squared. Based on the way we have defined x2 and y2, using the derivative function in the calculator, it's going to take it a while to compute. And I left off a square root. Silly me. All right, I'm going to start that part over. Square root. Alpha trace, there's that. And it is squared plus alpha trace, and it is squared. And then dx, or dt, I should say. dt, am I right? Am I right or am I right? I'm right. Okay, it's going to take it a minute to compute that. We're going to keep reading while it does it. Find the displacement vector for the skunk on the interval from 0 to 10. Displacement is going to be the integral from 0 to 10 of the velocity. So 2 cosine of 2t, not squared. I don't know why I put parentheses on that one. This thing's still thinking. So this is the x displacement. Notice we're using the derivative. I'm looking off the screen at this right here. The derivative, the derivative squared, and then the derivative squared. This guy's still thinking. So there's the x component. Here's the y component. 1/3 t minus, we'll write it this time, t squared over 6 sine t. dt. And we'll figure that out in a minute. Waiting on you, calculator. There we go. 39,684. Let's put units on this, though. Almost read it in the wrong place. 39,684. That is the total distance traveled, and it is meters. All right. Move this a little bit there. There we go. Slide this back. Okay, I want to find the displacement, which is those. So math, 9. 0 to 10, alpha 2, there's that guy right there. Waiting on you, precious. 0.913, and then the next one, second enter. There's the y2 part. Negative 13. 985. I know just kind of watching me type that in the calculator is a little bit on the dull side. I do recommend you try it just to get the familiarity with some of the buttons and the shortcuts and things like that. You've seen them a million times, but the faster you get, the better it'll be. Find the speed of the skunk. The speed is a number, and that would be, well, the speed. Notice it's the absolute value of velocity, because in speed, you could be moving forward, moving backward. You count it as positive. So we're going to do that. Square root of the derivative, which we've written a million times before, 2t, and it is squared, and then plus the square root of the other one, 1/3 t cosine t minus t squared over 6 sine of t, and it is squared. And we're going to evaluate all that. I should have put a 6 in there. Oh well, it's all right. I'll do it this way. With a little bar says t equals 6. So let's do it. Basically, it's like me plugging a 6 into all those t's right there. So let's go. Square root of y2, x2, evaluated at 6. And that whole thing is squared. Let's start over. I made a mess of this thing. All right, square root of. I need parentheses around everything that's about to happen. x2, evaluated at 6. Parentheses again, and then square it. That takes care of all this. Plus, back out of that, parentheses, y2 at 6, square that one, and I get, please get 3.9, yeah, 3.973. All right, speed, what do we measure this in? Meters per minute. It's a pretty slow skunk. Not that we want him to move very fast. I put meters per second. I'm glad he's not moving that fast. Here comes a skunk. He's gonna spray us quickly. Here he goes. Acceleration vector for the skunk at t equals 6. All right, time to figure this thing out. Acceleration vector, final answer, is going to be a number because they told us where to evaluate it. So we're going to do that. And y equals, I already have, lucky us, the second derivative, which is x3 and y3 in there. So I turned them on, press enter on the equal marks and turn them on. And straighten this paper up because it's crooked. Sorry about that. And then we shall back out of there and find out what the x value is at the third derivative at 6. Figure it out. 2.146. And then that one at 6. Whoops. At 6. Negative 4.323.